Okay, so it's chapter 9. So in this chapter, I'm going to introduce you the concept of phonon. Okay, so what is phonon? Basically, phonon is just the lattice vibration, but we quantize it. We quantize the phonon vibration. Okay, we know that this is the model of the atom arrangement. This is a model of atom arrangement. Okay, we have two models of atom arrangement, and then at different temperature, the atom in that arrangement will vibrate with different degree of freedom, right? So when we place the material or the crystal in the relatively cooler environment, then the atom will vibrate with the smaller degree of freedom. However, when you increase the temperature, then now the environment become hotter, then the atom will vibrate with larger degree of freedom. Okay, so the vibration mode of all these atoms is related to the vibration mode of the lattice, and we call this type of the lattice vibration phonon. Okay, so in this chapter, I'm going to introduce you the phonon concept by using two types of the model. The first model will be monoatomic model, that the atom in the solid composing only one type of the atom. The other model, the second model, will be diatomic model, that the model will contain of two types of the atom with two different masses. Okay, so this is a synopsis for this chapter. Okay, the first question that come to your mind may be, why do we study lattice vibration, or in other words, the phonon? When the lattice is at equilibrium, each atom is positioned ideally at its lattice side. Okay, so there's no vibration, there's no movement of the atom, and this only happens when temperature equal to 0 K. This is not okay, but 0 Kelvin. Okay, 0 Kelvin. Whenever the temperature is larger than 0 Kelvin, the lattice or the atom attached to the lattice will vibrate. Okay, whenever you increase the temperature, it will vibrate with larger degree of freedom. Okay, it's only static when the temperature is 0 K. At this moment, it's not possible for us to cool the temperature up to 0 K. Okay, 0 K is minus 273 degrees Celsius, which is very low. All right. So now we can assume that, like in at the room temperature, the atom in the solid always vibrating. Okay, but we just cannot detect it using our eyes, cannot. Kita tidak boleh tengok dia dengan kami mata, because we cannot detect the small vibration degree. Okay, at the room temperature. And the other thing is that the atom also very small, then of course you cannot detect the vibration. But in fact, at any temperature other than 0 K, the atom always vibrating. Okay, so when the atom vibrating, it can vibrate in 3 dimensions. So either vibrating X direction, that means that vibrate from here, left and right, left and right, left and right, and then Y direction, up and down, up and down, up and down, and Z direction, in and out, in and out, in and out. It will vibrate in 3-dimensional, and then it will vibrate in 3 directions simultaneously. So when the atom vibrate, then the atom will displace. Okay, the atom will displace from, let's say, vibrating in the X direction, then it will displace to X, positive X, negative X, positive X, negative X, positive X, negative X. Right? So it will vibrate from its equilibrium position, from the initial position, by a small amount. Okay, this small amount depends on the temperature. Okay, if you increase the temperature, then this small amount will slowly increase. So due to the force acting on this atom, it will tend to return to its equilibrium position. What that means? Okay, we know that in last chapter we have studied the chemical bonding, right? Chemical bonding means that all the atoms are bonded by chemical bonding, and we have 5 different types of bonding. For the example, now if you look at the copper, okay, Cu. So copper bind with another copper with the let's say the metal bonding. Okay, metal bonding. So when this atom, let's say atom R, is trying to move upward, then the neighbor or the nearest atom will try to pull it down to the original equilibrium position. Why? Because they have the bonding between them. You can just imagine just like spring. So when we have 3 ball that connected by the spring, so if this ball move up, then these 2 balls will try to pull it back to the original position or the equilibrium position. This is what it means by due to the force acting on this atom, it will tend to return to the equilibrium position. And this force is actually created by the chemical binding. Okay, so when it moves down, then you see it have the environment temperature, right? So it will still be moving up. So pull down, pull up, pull out, pull up, pull up, pull up. Then it create the vibration along the y direction or z direction or x direction. Okay, and then we call this lattice vibration, or in other words, we call it phonon. Okay, so due to the interaction between atoms, in fact, we have studied what type of interaction exists in the particular atom arrangement. So we have ionic, covalent, van der Waals, matter, and hydrogen. Okay, so all these are categorized as a interaction between atoms. So the various atoms can move simultaneously. So we have to consider the motion of the entire lattice. In the real crystal, the atoms are not fixed at the rigid side on the lattice, but are vibrating, except when temperature equal to 0 K. So in a periodic structure, the vibration have a waveform. Okay, so let's say the atom vibrate up, down, up, down. If you consider only, okay, the atom will vibrate in 3 directions. Okay, x direction, y direction, 3 direction, because solid exists in 3D space. Okay, 3D space. So it will vibrate in x direction, y direction, and z direction. But to simplify the calculation, and because I just want to introduce you the simple concept. So I will only take that this atom only vibrate in 1 direction. I will start from 1 direction. Okay, if it vibrate in 1 direction, then we can consider that, okay, let's say it vibrate up and down, up and down, up and down, and it vibrate with certain pattern, or we call it order. Okay, and if we have certain pattern or order, then we can reform this type of the lattice vibration